Great. So welcome to the blood-brain barrier section. As Deborah said, I'm Doug Spracklin. I'm here with my partners, Chris Schaefer and Travis Wager. We all work together at Pfizer. Just as a show of hands, I mean, the material is what it is at this point, but sometimes knowing who the audience is helpful in terms of how we frame things. By show of hands, how many people are from sort of a medicinal chemistry background? Okay. Biology? Okay, this is different. Something else? Okay. So typically in the past, we've had mostly chemistry-based audiences, so we'll see how this goes. So I'm going to first of all talk about the ADME challenges around CNS targets and start off, and hopefully at the end be able to direct you to the answer to this question as to whether CNS targets represent more difficult ADME space. And I've divided the talk into two parts. The first, I'm going to talk about just some basic physiology of the blood-brain barrier and really focus on efflux and specifically PGP, which is of interest, high interest to people working in this therapeutic area. And in the second part, I'm going to talk about a couple different project strategies and how the nature of the targets themselves influence the ADME strategies. So we've been working on the blood-brain barrier for some time. It still remains a challenge. So hopefully if I do this right, you'll know the answer to this question by the end of my talk. But just in case I don't get there, the answer is yes, it is still a pretty difficult problem. We've been working on it for a very long time. The way I want to talk about the first is that I'll give a little bit of background of the physiology and talk about why it is such a difficult target to work against. I'm going to largely base the talk around this MegaMouse study. This is a large collaborative study we undertook at Pfizer some time ago, and we've divided up the results into both an in vitro and an in vivo section, and then finally wrap up with some conclusions. Okay, so what makes the blood-brain barrier difficult is the underlying physiology, and specifically it's the tight junctions. So on the left-hand side is an electron micrograph, and it shows, it's pretty hard to see here, but the starred area represents the tight junctions. And on the right-hand side that you can see that there's a cartoon of what they look like, and in fact you can see that there's overlapping around it, and that's what creates the tight junction or the barrier nature. If you compare a brain capillary on the left to the peripheral capillary on the right, the tight junctions are shown here, and again you see the overlap. And in comparison to the peripheral capillary, you actually have these fenestrations or openings. So this tight junction is what makes it impervious to the normal transit or the ready transit of drug molecules. So just some properties of the blood-brain barrier. There's nearly 400 miles of capillary that accounts for about 1% of the brain volume. Blood approximates 3 to 5% of the brain volume, and that can be important in how you interpret your data. The surface area of the blood-brain barrier is nearly 1,000-fold greater than the blood-CSF barrier, and I'll illustrate that later on. The brain gets up to 20% of the cardiac output, and what's been of interest to ADME scientists is that we know there's metabolic events, both phase 1, P450, and phase 2 metabolism, and what's been of high interest over the last several years is the active transport, both the absorptive and the efflux mechanisms.